Today we just illustrate a resonance effect by taking an example. Okay, I have two compound, just like one compound is this NO2, here also NO2, here also NO2. Okay, and another compound, this one. So the question is that among these A and B, which one undergoing nucleophilic substitution faster? That is the question. Okay, so how can we explain? Okay, we can just check. Okay, so first we take our second compound. Okay, that is a chlorobenzene. This is our chlorobenzene. When you treat this with a nucleophile, okay, so we know that compared to aliphatic compound, aromatic compound undergo nucleophilic substitution less, right? Less in the having a less rate. Okay, so we want to enhance the rate of this nucleophilic substitution. Okay, so here this nucleophilic substitution less susceptible. If it is happen, how it is? So it will attack, okay, in this position. Okay, but it is less facile in this stage. Okay, what about our second compound? So we can see chlorine here, okay, and here you have NO2, right? NO2 minus plus. Okay, here also NO2. Okay, here also NO2, right? Now what is the meaning of this NO2? We know that NO2 is electron withdrawing group, right? So why in first situation, why it is not undergoing nucleophilic substitution? We know that benzene ring as such electron rich center, so it won't undergo a reaction with another electron rich reagent, that is, it is less facile in this case. So in order to enhance the rate of reaction, we just introduced electron withdrawing group at 3 different positions. Okay, that is 2, 4, 6 position. Okay, right. Now we can see the rate of reaction much enhanced. How can be explained? Okay, so it can be explained by means of resonance effect. So what will happen? We can just go through that one. Okay, so first we take the compound Cl. Okay, Cl. Okay, now NO2. I am taking one of the NO2 as whole. Okay, plus, okay, double bond. Okay, now your nucleophile comes to the picture. Okay, nucleophile attack at this center. Okay, at this center, what will happen? So a new bond is forming between this nucleophile and this center. So in transition state, okay, so you should shift this pi bond to this carbon. Okay, so your Cl here, nucleophile here. Okay, now N double bond O minus plus minus charge. Okay, right, double bond. Now due to the presence of this NO2, what will happen? This negative charge again move toward this NO2 functional group. That is the importance of the presence of this NO2. Okay, so now you can, so here also NO2 here, okay, here also NO2, okay. So here now you can have Cl nucleophile, right, double bond N O minus, okay, plus double bond, okay. So NO2, now in the next step what will happen, this come back to the ring, okay, this come back to the ring. So this shift onto this CC bond, and this pi bond move on to this carbon. Now the same phenomena we can see through this NO2, right, through this NO2. Ready? Now after that you can have a structure like this. Cl nucleophile, here your NO2, double bond, here your NO2, N, double bond O minus, plus, okay. Now your negative charge here, right? So what will happen, this negative charge shift on to this Cn double bond, and this double bond move on to this oxygen. Now finally you can have a structure like this, Cl nucleophile, double bond, here your NO2 is here, here your NO2 is here. Now here what will have, double bond N O minus, plus, right. Now what will happen, again it is come back to the ring. So shift, okay, and this move on to this carbon. Now what will happen, again it will undergo another kind of resonance. Cl nucleophile, NO2, double bond, okay, here NO2, here NO2 like this, double bond O minus, plus. Now your charge is here. The same thing happened here, okay. So this electron withdrawing group enhance the rate of nucleophilic substitution. So finally what will happen, so I am not writing this resonance effect. Finally what will happen is that NO2 here, NO2 here, NO2 here, and Cl here, nucleophile here, okay. Now negative charge here, okay, double bond, sorry, okay, double bond, okay. Now this lone pair electron come back, and our chlorine get eliminated. Finally you will end up with the substituted benzene. So we can see nucleophilic substitution reaction in benzene in rare case. So one of the most discussed example is this one, and this kind of a complex is called a Meitner complex. Now your product will be so your product will be nucleophile substituted benzene, NO2, So resonance effect having many applications. This is the one of the discussed examples. So a presence of electron withdrawing group in benzene ring can enhance the rate of nucleophilic substitution reaction. So it is better to have strong electron withdrawing group. So we know that NO2 is strong electron withdrawing group. Okay. So another illustrative example, I'll just discuss. I have two compounds. Says this and this. Question is that among these two hydrogen, which hydrogen is more acidic? Okay, so acidic means that there should be a dissociation, right? So this, suppose this species is acid, means it should donate H plus. How it is possible? This bond should cleave like heterolytically. Okay, so you should end up with this compound plus H plus, and here if it is happening, you should end up with this and H plus. Now how can we predict among these which one is more acidic? You just check whether this conjugate base or this conjugate base are more stable, right? More stable. So how can we explain? That you can explain by means of resonance. Here you can expect resonance, here there is no resonance. We know that this is cyclopentadienyl anion. It is aromatic in nature. Aromatic means there you can expect resonance, right? So this lone pair electron shift, that time this pi bond shift on to this carbon atom, that thing happens. So this is highly stable. So cyclopentadiene is much acidic compared to cyclopentane. Okay, clear? Thank you. Take care.